what I'm going to do for today is going to cover a quirkier version of what I have for Lewis diagram in the video that I posted. And I hope that we can get into a pretty decent solver simply by looking at it for today, and then we'll come back in. On Wednesday and Friday, we'll go into the geometry, the structure, and so on. So the quick explanation is that a Lewis diagram is a representation on how to draw a chemical bond. And we're going to extend from Lewis diagram to actually predict how the molecule is actually shaped. So that's going to be what we're going to focus for today. So we're going to try to focus on Lewis diagram. And essentially we're going to go through this handout, and by the end of this handout we'll have a pretty decent example on where we are going to be at the end. I might skip the molecular orbital and so on. There's a series of videos that I already posted. If you want to go into much more detail, you can watch them. But this is just kind of a much more truncated versions on just the necessity and information. Now, essentially, molecules, if you remember, if you have n equals to 2, you'll find that, for example, this particular shell from the previous exam should fit 8 electrons, for example. And essentially, a chemical bond is going to do just that. That is, if you n equals to 2 can fit 8, but for example, you might only have 7 electrons or 5 electrons and so on. And essentially, your molecule then would like to fill in all of these empty orbitals to go all the way to 10 electrons total, or 3 positive, and because your molecule doesn't have as many electrons as it would prefer to have, it's going to try to share electrons to get what it needed by creating a chemical bond. And the fundamental that you need to know when you're looking at the periodic table is you want to know what is the number of the valence electron. So this is the one that's important, the valence electron. And there's an easy way to figure out what the valence electron is from a particular periodic table. So if you have a periodic table that looks like this, you simply have to count from the left to the right. That is, hydrogen have 1 valence electron, and if you see what the group number is, it's going to be group 1a. So it's going to have 1 valence electron. If we have magnesium, which is right here, it's in group 2, so it's going to have 2 valence electrons. It essentially tells you the number of electrons in the outermost shell. Yeah? So this is our periodic table. What is the valence electron in sulfur? Thank you. Sulfur is here, and it's going to be 6A. Or if you kind of forgot, just kind of go 1, 2, then forget about the transition metal, 3, 4, 5, 6, 7, and 8. Okay. So that's kind of what we do. So if we were to go to look for, say, bromine, which is right here, then the valence electron is going to be the same number of its group, so it's going to have 7 valence electrons, and so on. And essentially, that's kind of what I want you to do for today now. So if you look at carbon, carbon is going to have 4 valence electrons, and we've already done sulfur. Sulfur is going to have 6. How about oxygen? How many valence electrons does oxygen have? 6. Chlorine, nitrogen, hydrogen. Okay, good. And among other things, these are the ones that you're going to see quite a lot. And if you remember some of the valence electron by head, then it's so much easier to do the Lewis diagram. There's a head in the front, so you can come up in front and grab one. We're going to work on these for today. It's a truncated version of the Lewis diagram. So there's a lot of different ways to try to draw a Lewis diagram, and we're just going to jump right in. And this is the one that I find work a lot always, which is whenever you have to try to draw a Lewis diagram, calculate first the number of bonds. And if you already start to do some of the practice problems and so on and look at the solution key, you'll see that I do the same thing on my solution key as well. So in order to calculate the number of bond, what I'm going to try to calculate is first the numbers of electron first. And I'm going to add up all the valence electrons. So carbon, in the molecules of CH3Cl, carbon have 4 valence electron, and again you have that one. Hydrogen have 1 valence electron each, and there's 3 of them, so I'm going to multiply it by 3 because there's 3 hydrogen. Can you guys see it on the back, my numbers? Or is it a bit too small? Yeah? Okay. And then if you look at chlorine, chlorine has 7 valence electron. So it is going to be 4 plus 3 plus 7. You have in the end 14 electrons in total. Okay. So these are just the number of electrons inside all of the atoms combined. And you have 14 electrons total. Now, the thing is that your molecule prefer to have a different number of electrons in total. So carbon, so I'm going to use a different color in this case. Carbon prefer to have 8 electrons, because if you look at carbon, it's in n equals to 2, so it can go all the way to 8 electrons in total. Usually this is called the octet rule, that you can fit at 8 electrons, so you can, each of the molecule prefer to have 8. Yeah. Okay. Alright, so carbon prefer to have 8. And the reason why carbon prefer 8, if I were to look at here, I look at where carbon is located. And in fact, majority of the time, you can just assume that it needs to go all the way to the n. And by n equals to 2, you have in the end 8 electrons as your valence electron here. So you want to go all the way to the n. So carbon in this case prefer to have 8 in total. But if you look at hydrogen, which is right here, hydrogen can only fit 2 electrons because it's the first electron shell, quantum number n equals to 1, so it only fits 2 electrons. So if you want to remember anything for now, just remember most atoms prefer to have 8 electrons. One of the exceptions is hydrogen, and hydrogen prefer to have 2 electrons in total instead of 8. That's because of the quantum number n equals to 1. Okay, most material prefer 8 electrons, and in this case hydrogen though prefer only to have 2 because the quantum number is just n equals to 1. It can only fit 2 electrons in total. And the last one here I have chlorine, and chlorine also prefer 8 electrons. The thing is, so if you add everything together, so you have 8 plus 6 plus 8, you should have in the end 22 electrons. Yeah, I'm not calculating it incorrectly. So you see, your molecule all prefer to have 22, but they only have 14. They prefer 22, but they only have 14. So they need to share the electrons by making a chemical bond. And you want to do that by simply looking at the difference. So the difference between 14 and 22 is 8. And you divide it by 2. This particular molecule should have in the end 4 bonds in total. So far so good? Your preferred number of electrons, your actual number of electrons, you look at the difference between the 2. The difference is 8 divided by 2. So this must be the total number of bonds that you have in the entire structure. So when I'm actually drawing the Lewis diagram, I'm going to put carbon in the middle. And I'm going to put hydrogen, and I have 3 of them. So I'm going to put 1 hydrogen here, 1 hydrogen there, 1 hydrogen there, and then I have a chlorine at the end. So I have 4 atoms, and I have 4 bonds to give. So I give it 1 bond here, 2, 3, 4. So far so good. Right? So we've already used up all the number of bonds that we have. Now we're just going to do them make sure that each molecule have the preferred number of electrons that it'd like to have. Okay, and the rule for that is that each bond counts as 2 electrons, because whenever you're sharing a bond, you're sharing the 2 electrons. So if I were to look at hydrogen, I'm going to highlight just the hydrogen here. The hydrogen molecule have a single bond, and each of the single bond counts as 2. So the hydrogen is going to have 2 electrons on it already. So the hydrogen is happy because this is exactly what we want to have. Each of the hydrogens are going to have 2 electrons. So the way I usually count it is 1 and 2. So I have 2 electrons on each hydrogen, and so that hydrogen is happy. The next hydrogen is also the same. It prefers to have 2 electrons, and I have 1 electron here, and I have the second electron there. So this particular hydrogen is happy. And so is this one. So I have 1 hydrogen here, 1 electron there. So this hydrogen is happy. So how about the carbon? So let's count the number of electrons around the carbon. Does it have exactly the number of electrons that it wants? Sorry, let me erase some of these things. Right, so the hydrogen is happy. So let's see if the carbon exactly have the number of electrons that it prefers to have, which is 8. So I'm going to count around the carbon here. I have 4 bonds. So 1, 2, 3, 4, 5, 6, 7, 8. So for the carbon, I have 8 electrons around it. So, which is what it wants. It prefers to have 8, so it's happy. The last one here is the chlorine. And the chlorine also prefers to have 8. And if you try to count the number of electrons in the chlorine, which is this one here, what you'll find is that so far there's only 2, which is 1, 2. So I need to give it 6 more electrons, and I'm going to do that by giving it some lone pair. So I need to give it 6 more electrons in total. 1, 2, 3, 4, 5, 6, 7, 8. So this whole thing is now a complete Lewis diagram of CH3Cl. Once you kind of try to do this, it's actually quite quick, and I'll show you a much quicker method than trying to do this again. Yeah?
So when you're drawing the Lewis diagram, you're drawing
That's a good question, and the answer is you exactly have 14 electrons in total. If you count the total number of electrons, you'll find that there's 14. We can try to count it too. I use blue for the total number of electrons. What we calculated there is just how many electrons do we actually have, and we only have 14. So if you count the number of electrons here, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So we have 14 electrons, which is exactly what we have. Yeah. We've already back calculated that, and we know the total number of electrons since we already calculate the total number of bonds. And we just count all the way to 8 or to 2, depending on what it prefers to have. I found that it may be slightly different, but since you guys already have to calculate the valence electrons anyway, I found that this is actually pretty consistent. And it works wonderfully well once you go into extended octet, which I'll explain later. Yeah? Mm-hmm. Yep. So 8 divided by 2, and then we'll do another one. We'll do another example. In fact, I want you to try to do this one on your own. So the molecule that we have is COH2. Let me actually write this bigger, because that's a bit too small. So what is the valence electron on carbon? 4. Oxygen, hydrogen, 1 each, and there's 2 in total, so 1 times 2, because they have 2 hydrogens in total. So the sum of it is going to be 12. Yeah. The prefer. Carbon prefer to have 8 electrons. Oxygen prefer to have also 8. And essentially, most of the time, you're going to find that they prefer 8, except for hydrogen, which only prefer 2. And of course, there's 2 of these. So 8 plus 8 plus 4, 16 plus 4, we have 20. So how many bonds that we have? 4 bonds. The difference between 20 and 12 is 8 divided by 2, so we have 4 bonds. Okay. So let's continue with this one. So I have carbon, and I'm just going to equally spread all the molecules. I have 3 molecules in total, so I'm going to spread it into 3. Right. So I'm going to give one bond each. But you see, I need to give it 4 bonds in total, so I need to give 1 more to go. And remember, hydrogen prefer to only have 2 electrons, and 1 bond is enough for hydrogen. So I'm going to give the last bond to oxygen. And if you see a double line like this is called the double bond. Just because you have 2 lines. Okay? So my question is my hydrogen happy? Does the hydrogen have exactly the number of electrons that it wants? The answer is yes. So it has 1 and 2. So around this hydrogen, there's 2 electrons. So the hydrogen is happy. And let me try to highlight that. So around this hydrogen, there's 1 electron and 2 electrons. And it we've already calculated that each of the hydrogen prefer 2. So, and it does have 2 electrons. So it's pretty happy. If we look at the carbon, I'm going to circle around the carbon now. My carbon prefer to have 8 electrons, and if I count the number of electrons here, I have 1, 2, 3, 4, 5, 6, because this is double bond, 7. So my carbon has 8 electrons. So the carbon is happy as well. So hydrogen is happy, carbon is happy. But the one that they're not yet happy is the oxygen, because so far you only have 1. If I look at this oxygen here, there's only 1, 2, 3, 4, and it wants 8. So I'm going to give it 4 more electrons. So 1, 2, 3, 4. Okay. And this is going to be the complete, this is going to be the complete Lewis diagram of this molecule. So I'm just going to count exactly to whatever number it prefers to have. You want to have 8 electrons, so oxygen, initially this was not there, and then the oxygen there's only 1, 2, 3, 4. So I'm going to give it all over. Okay, we're just going to count to 8, which is a bit more easy to do. It's quite consistent. Any questions in terms of the method so far? Yeah. It seems like there's a lot of calculation to do, but in the end of the day, it's actually pretty straightforward. I'll give you now a much quicker version. There's a handout in the front that you just came in. And essentially, you're going to try to do, instead of calculating all the number of bonds, the quickest way to go is calculating the most likely charges and the most likely number of bonds. Now, I put a caveat of most likely, because it's not going to be always the case that it have X number of bonds. So if you look at the charges, and we go back to the periodic table here, the most likely charge is going to follow a rule, if you remember from oxidation number, hydrogen prefer to have a +1, the second row +2, how about this row? Should be +3, carbon is ±4, -3, -2, -1, 0, right? And essentially, if you copy this out, it's going to be correlated to the preferred number of bonds. That is, hydrogen prefer to have 1 bond. Carbon prefer to have 4 bonds. Fluorine prefer to have 1 bond, and so on and so forth. So let me just kind of put that on the bottom to the one that I wanted to fill in. So the most likely charge on carbon is ±4. So the most likely bond in carbon is going to be 4. Just the absolute value. Hydrogen is most likely going to have a +1. So the most likely number of bonds is 1. Fluorine, which is F, is going to be -1 charge. So it's going to have 1 bond. Nitrogen is -3. So it prefers to have most likely 3 bond. Sulfur is -2. So it's going to most likely have 2 bonds. Yeah. So it's just Let me see if I can use a different color here. I'd really just kind of go +1, +2, 3, and so on. So this is going to be +1, +2. Oh, too big, too wide. +3, plus and minus 4, -3, -2, -1, 0. And that's going to be more or less what you have in terms of the preferred number of 1. 1, 2, 3, 4, 3, 2, 1, 0. Halogens or the noble gases prefer to have 0 bonds, most likely. But again, I can't stress enough, and I keep saying most likely. So this is the quickest way to draw the Lewis diagram by looking at the most likely number of bonds. Not going to be true all the time, so this is what we're going to do. So we have a molecule of HF. So the first thing I'm going to do is to draw a hydrogen and a fluorine. So what is the most likely number of bond of hydrogen? 1. Fluorine is also 1, so I'm just going to connect it 1 to 1. Hydrogen have 1 bond, fluorine have 1 bond. So they're happy with the bonds that they have. But remember, some molecules prefer to have 8, and hydrogen prefer to have 2 electrons. So I'm just going to count the number of electrons that they actually have again. So hydrogen prefer to have 2, so there's 1, 2, so hydrogen is happy. But if I were to look at the fluorine, they prefer to have 8 electrons, but so far there's only 2, so I'm going to give it 6 more to go. Right, so this is the quickest way to draw the Lewis diagram. You remember the preferred number of bonds, and you go from there. Alright, so let's do the next one. So we have NH3. So the first thing I'm going to do is just going to draw nitrogen, and I'm going to spread out the hydrogen. So hydrogen here, hydrogen there, and hydrogen here. So what is the preferred number of nitrogen in terms of number of bond? No. Nitrogen. Nitrogen, did I put it here? Nitrogen is going to have a -3 charge, so it's going to prefer to have 3 bonds. So I have 3 hydrogens, so I'm going to give it 1, 2, 3. So now the nitrogen is happy with the bond. The hydrogen is happy with the bond, but remember, nitrogen wants 8 electrons. So far, the nitrogen only have 1, 2, 3, 4, 5, 6. It wants 8, so I'm missing 2 more, so I'm going to put a couple more down. Yeah? We're just counting to 8 most of the time now. Okay, so CH2F2. There, you can draw the Lewis diagram however you want, but I have a suggestion that I want you to try to follow. Whenever you have a molecule, especially for carbon and so on, try to group the same molecule in the same corner. So draw the same element in the same corner. What I meant by that is that I have 2 hydrogens, so I'm going to put the 2 hydrogens right here on the same corner, and the 2 fluorine, fluorine is purple usually, on the same corner as well. Yeah. You can draw it whatever you want, but later on we're going to have to calculate polarity, and once if you try to do it this way, it's so much easier to do molecular polarity. Okay. So I have carbon prefer to have 4 bonds, and I give it 4 bonds because I have 4 molecules attached to it. Fluorine prefer to have 1 bond, hydrogen prefer to have 1 bond. So far the number of bonds is okay, but remember, fluorine prefer to have 3 electrons, but so far we only have 1. So I'm going to give it 6 electrons in each fluorine. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And if you want to count all the way to 8, then the last 2 is right there. Right, so each bond counts as 2 electrons. Yeah. The preferred number of bond? So let me split this over a bit. fluorine prefers to have one bond, and then we have one bond. Hydrogen prefers to have one bond, and it's fine. Carbon prefers to have one bond, okay? And the next, we're just counting all the way to 8. We want to get all of it to 8. So 1, 2, 3, 4, 5, 6, 7. And we do the same thing for the rest. Yeah?
So the general rule is whatever the charges they for the bondage, regardless of negative or minus.
Yeah. And again, this is the most likely. I can't emphasize that enough. Most likely. Yeah. Any questions about this one for now? But yes, you disregard the charges. The charges will come back in again once we have like multiple or very similar structures, which is called the formal charges. But we're going to get that in a bit later. So if I were to have a molecules of CH2S, what I have again is carbon, I have sulfur, hydrogen, and hydrogen. Again, I'm going to put it in the same corner. And then, or if you want to kind of spread it around, that's fine too. Hydrogen prefer to have one bond. Hydrogen prefer to have one bond. So how many bonds does sulfur prefer to have? 2. And your Lewis diagram more or less should look something like that. It looks kind of funky, but that's all right. If you want to draw it this way too, that's fine. Sorry? Oh, I forgot about that at all. So the central, by the way, I'm adding 4 more electrons on the sulfur to get all the way to 8. So Melody asked me about which one is the central atom. So in this case, I'm going to put carbon as the central atom, but why? The reason for that is that the central atom is going to be the one with the least electronegativity. Okay. Except hydrogen. So essentially, your central atom is always going to be the least electronegativity, but not hydrogen. So if you remember, what is the order of 9 most electronegative element in the periodic table? I gave you guys the phonetic, right? Falkland-Birch? Yeah? So Fo, F-O-C-L-N, Falkland, Bryce, B-R, sorry, S-C-H. So I'm going to exclude hydrogen from being the central atom. So I have carbon or sulfur in the central atom. Carbon have less electronegativity, so it's going to be in the center. Okay. And majority of the time you see carbon is going to be in the center. So carbon is less electronegativity, is going to be in the center. So I have carbon, hydrogen, sulfur. So carbon is going to be the center because I have to exclude the hydrogen. The reason for that is the hydrogen can't fit any more electrons than 2, so you can't make any more bond. Yeah? No, sorry, this is, fluorine is the largest. Carbon is going to be less. Right. So this is going to be 9 of the highest electronegativity. So the highest electronegativity of all the elements is fluorine, oxygen, chlorine, so on. Falkland-Birch. Most of the time it's actually pretty straightforward to know which one is the central atom. But if you remember Falkland-Birch, just Falkland-Birch and write it down somewhere in your exam. It's pretty useful because we use it so many different times. So this is the quick way in terms of drawing the Lewis diagram, but it doesn't work all the time. That's why I keep saying that it's most likely. And so I'm going to tell you when it doesn't work. One of the times that it definitely does not work is when you have a net charge. And expanded octet. which is what I'm going to cover in a bit more, maybe tomorrow, or Wednesday, excuse me. So as long as your molecule have a net charge, the most likely number of bond doesn't work very well. So here are some of the example of the common one that you have in the laboratory. So we can have a molecule of NH4+, CO3 2-, which is carbonate, and so on. So let's try to do this one. So whenever you have a charge, just try to calculate the number of bonds, and until you get used to it. And after a while, you'll realize that you don't have to calculate every single time. You'll start to remember how many bonds that they prefer to have. So let's do the nitrogen here. So nitrogen prefer to have 3 bonds, right? But we have 4 hydrogens in total, and nitrogen prefer to only have 3. So you can see that immediately there's not enough bonds. So that's why it doesn't work if you have a charge, especially like a +1, -1, and so on. So in this case, we kind of have to calculate the number of bonds again. You'll know that it's going to be in the end 4, but let's just do the exercise while we're at it. So nitrogen have 5 valence electron. If you look at hydrogen, each of the hydrogens is going to have 1, and I have 4 of them. So 1 times 4. And there's going to be something else though. If your molecule have a plus charge, so in this case a +1, it means there's 1 less electron. Right? That's why you have a plus charge, because you have a lack of electron. So I'm going to subtract this by 1. So I'm going to subtract it by 1, because this is a plus charge. Plus charge means 1 less electron, so I'm going to subtract it by 1. So in the end, the valence electron that I have is 9 plus 4 minus 1. So I have, 5 plus 4 minus 1, which is 8 electrons. Okay. The key there is that you have a charge, so you have to subtract it by 1. And how about the prefer? Well, nitrogen prefer 8, and I have 4 hydrogen, and each of the hydrogen prefer 2. And that's going to be the same. So 8 plus 8 is going to be 16. The difference between 6 and 8 is going to be 8 divided by 2, so I have 4 bonds. Okay. So I have 4 bonds now, and you can see that there's 4 hydrogen, so immediately it's clear that you have enough. So let me finish the Lewis diagram here. Let's use orange, because we haven't used orange. So nitrogen in the middle, I have 4 hydrogens, so I'm going to put them, distribute them equally. And I have 4 bonds to give, so 1, 2, 3, 4. I have 4 bonds, and I already give everything a single bond. But there's one last thing that you have to do if you have a charge. Right? If you have a charge like this, put everything in a bracket, and put a plus charge in the end. So this is the proper way of drawing the Lewis diagram when there's a charge. Put everything in a bracket. And you can see again here, my point is that the most likely number of bonds doesn't work. Because nitrogen prefer 3, so most likely have 3, but this is just a start. It's going to have 4 instead of 3. Yeah.
So let's not prefer one and not, look at the chart.
No, because the nitrogen doesn't really matter what is +1, +3. It's still prefer in the end to have 8. Yeah. Oh, if you look at nitrogen, is to the right of carbon in the periodic table. So carbon is 4, nitrogen is going to be 5. Yeah, group is valence electrons. So in this case, nitrogen have 5 valence electrons. Okay, so I'll do one more, and you'll find that they're all very similar to one another. Maybe a couple, we'll see. So let's do CO3 2-. I'm going to give myself extra space just because I'm writing bigger than I needed. So we have CO3 2-. The valence electron of carbon is 4. The valence oxygen is 6, and I have 3 of them. But I also have a plus charge, and a minus charge here. And whenever you have a minus charge, it means you have an excess electron. and specifically you have an excess of 2 electrons. That's a minus charge, this is excess electron. So I'm going to add it by 2. So this is going to be 4 plus 18 plus 2. So it's going to be 24 electrons in total. So in the end, we have 24 electrons. If we were to calculate the prefer, carbon prefer 8, and each of the oxygen prefer 8, and there's 3 of them. So 8 plus 24 is 32, and the difference between 32 and 24 is 8 divided by 2, so I have 4 bonds. Okay. Carbon will most likely have 4 bonds. We'll get to in a bit more where it's more than 4 and less than 4. Yeah? I basically look at the periodic table. If you count the periodic table, if you look at where carbon is, and you look at the column, you can count 1, 2, 3, 4, 5, 6, 7, 8 all the way to the end. So I can add 8 electrons in total. So that's kind of most likely what it is. You're trying to fill all the available space in the electron shell of the carbon molecule. You can see it goes from group 1A to group 8A, so that's why it's 8. We're going to go to in a bit more where it's not 8. I'll give you one example today as well. So let's just try to finish off this particular drawing. And I have carbon in the central because it's least electronegative, and I have 3 oxygen, so I'm going to distribute it equally around the drawing. And I have 4 bonds to give, so I have 1, 2, 3, so I need to give 1 bond somewhere else. Doesn't really matter which one. Okay, and the rest I'm just going to count to make sure that each of my molecule have 8 electrons. And you can see that carbon have 4 bonds and each bond is 2, so carbon is happy. But the oxygen is not. So this oxygen only have a single bond, so I need to give it 6 more electrons. This oxygen only have, let me kind of make this a little bit more clear, have a single bond, so I need to give it 6 more. Oxygen on the top have 2 bonds, so it only have 4 electrons, so I'm going to give it 4 more electrons to go. I'm just counting all the way to 8, because that's 8 is the preferred number. And because we have a charge, I'm going to put everything in a bracket and put it as -2. Because they have a charge. So far so good? Yeah. It's quite repetitive, and after a while you don't need to do the counting anymore. Once you get used to it, you can know like, oh, it's going to be 1, 2, 3, 4, and so on. But in any case, the little bit of counting works fairly well. Now, there's one other thing that I want to mention in this particular structure. That's why I chose CO2. There's no particular reason that I'm going to get a double bond here. I can have a double bond there, like that. And if that's the case, then we're going to have a slightly different Lewis diagram. So I can have a Lewis diagram that looks like this, for example. And in fact, I have 3 different combinations possible. Sorry? No, the double, I want you to notice the location of the double bond is different on each of these structures. Let me actually... sorry? Kind of the same, and kind of doesn't matter, and kind of matter. So, here, these are all what we call the resonance structure. Now, if you kind of simply look at it like, okay, why is it any different than the double bond here versus right there or up there? The reason why they're slightly different is because you can have isotopes. That this oxygen could be an oxygen 18, this one could be 19, this could be 20. In terms of, they may have different number of nucleus, in which case then where the bond is located is going to make a difference. And in fact, a lot of the time, if you have MRI and so on, one of the bonds is on an isotope, and that's why you want to make sure that if there is such an isotope effect, you want to make sure you know where the bonds are located, because that's when it makes a tiny bit of change, but we can actually make the difference when we actually try to measure. So they do have some differences, but mostly when you go into radiology and so on, or the isotope makes a lot of difference. But anyway, these groups, they look very similar, but the location of the double bond is different. And they're just simply called a resonance structure. Okay. Let's see. There's a couple more to go. SO2 minus. And I'm just going to give you the solution for now. We have a few more minutes to go. So this one is going to look something like this. If I'm not mistaken. Oh, actually, I'm not entirely sure that's right. Hold on. So 6 plus 6 times 2, so 6 times 2 plus 1. Oh, sorry, this is a typo, so that's why it looks kind of weird. So scratch that off the map because that's a typo. It's supposed to be 2 minus, but I'm not going to try to draw it right now. Sorry, it's just a typo. The next one is NO3 minus, and this one here is going to be 5 plus 6 times 3 plus 1, because there's a negative charge. So this is going to be 18 plus 6, so 24. Prefer is going to be 4 times 8 is 32, so you have 4 bonds. So the nitrogen once you have charges, I always double check my number. So NO3 minus would look something like that. And you can see it's once you get used to it, it actually doesn't take that long to do. But obviously, if you have to explain the step that you're doing, it's longer. But if I don't have to talk or anything, it takes me a few seconds to do it, just because I'm used to it. Hopefully, by the time you finish your laboratory, it becomes a little bit easier for you as well. Any questions about the Lewis diagram? Yeah. Right, so the difference is 8. 32 and 24 is 8 divided by 2, so I have 4 bonds. No, we didn't, because that's HF is, there's no charge, so you don't have to worry about the calculation at all. You can just follow the most likely charge. No, so here's the thing. This is the most likely one. This is most likely, but you notice that there's no charge here. The charge of the molecule are all 0. If they're all 0, it works perfectly fine. But once you have a +1, a -1, a -2, and so on, it doesn't work anymore. So that's when you kind of want to go back and just calculate it. When there's a charge, it doesn't work, so you have to calculate it. The calculation works all the time. Okay? So that's the thing. We're at 10:50, so let me kind of do some announcement, because otherwise I will forget. Let's take a few minutes. So the first things first is that we're going to have an exam. We're going to have exam number 4. 3 or 4? 4, I think. And it's going to be a second to last day of instruction, which is going to be, I believe, December 3rd, or December 5th, excuse me. Okay. No, sorry, December 5th. Okay, so December 5th, we're going to have an exam, and it's basically going to be about Lewis diagram, because it's one of those things that in chemistry that you really need to master. So it's going to be about Lewis diagram, geometry, as well as polarity. Okay. We're going to remove colligative property altogether. So essentially, colligative property is anything under part 5. We're going to touch a little bit about intermolecular interactions because it's kind of important as well. But we'll see how fast we can go or how much we can cover. I'm going to remove some of the molecular orbital diagram theory and so on, just kind of mention it in passing. But essentially, your exam number 4 is going to be December 5th, Lewis diagram, geometry, and polarity. And if you want to work ahead in terms of extended octet and so on, the video is already up online. But of course, we're going to do some more practice like this next week as well as in the laboratory. And the other thing is that we're also going to have a final on December 12th, I think. December 12th at 8 a.m. Okay. And the final is going to be cumulative. And what I'm going to try to do is that we have one last day, the last day of instruction, where I'll give you guys some practice problems and so on. Or I'll give you practice problem beforehand, and if you want to work on it, or if you have a last minute thing or a last review and so on, that's when I'm going to go back in. December 10th is Monday. No instructions on Monday. Our last day is December 7th. Last day, December 7th. I'll update that in the syllabus because I think I put the exam on December 7th, but I'd rather do it on December 5th. I'll truncate some of the material on just the most important one, which is in this case Lewis diagrams and geometry and so on, and make best use of your time in the laboratory, which is the Lewis diagram labs. Try to get these things done so that when you come back in, everything else makes more sense for you. All right, so I'll see you guys later on Wednesday.